So, hello and welcome. My name is Thorsten Götte, and I'm a PhD student at Paderborn University. And today I will present to you the paper Time-Optimal Construction of Overlay Networks, with this joint work by me, Christian Hinenthal, my advisor Christian Scheidler, and Julian Wertmann, which are all from Paderborn University. So first things first, what do we talk about when we talk about overlay networks? So in general, an overlay network is a network that is built on top of another network. In our particular context, we will take a look at peer-to-peer networks. Those are overlay networks which operate over the internet. We model these networks by the so-called NCC0 model, which was introduced by Augustin et al. In this model, we have a fixed set of n nodes, which are the participants of our network. And all of these nodes have a unique and immutable identifier of size O of log n. This identifier can be thought of as the IP address of a node, in a sense that if I know the identifier of a node, I can send a message, just as I could with an IP address in real life. We represent that by these directed edges. So the directed edge here means that v2 knows the identifier of v1 and also knows the identifier of v3 and can therefore send messages to these two. Further, we assume, to simplify the analysis, that the communication works in synchronous rounds. That means a message sent in round I is received in round I+1. So most importantly, we greatly restrict the number of bits that a node can send in a given round. In particular, we say that a node can only send log n to the square bits per round. So the idea is that it can only communicate with very few other nodes and can send only very small messages to these nodes. So for example, what is possible in this model is to send these identifiers around. Since the identifiers are small, we can send a few of them around in every round. So for example, v2 could take the identifier of v1 and send it to v3 and vice versa. And therefore, it would establish a new communication edge between these two nodes. So starting from the next round, this could then also be used for communication. And therefore, we can create arbitrary peer-to-peer topologies, which are tailor-made for their purpose. However, what we cannot do in this model is to introduce big sets of nodes to one another. So for example, assume that v2 basically knows the ID of all the other nodes in the system, which is something which in practice could happen. You can store all the IP addresses there are on a single hard disk. However, what we disallow is that you can send a message to all of these nodes. So for example, what v2 cannot do is simply introduce all of these nodes to each other and build a big click. So this is something which you cannot do, because in practice, you also could not do that, because your network card would only allow you to communicate with like a small set of other nodes in a single round. Now, the problem we want to solve now in this model is the problem of overlay construction, because as all these overlays are based on IP addresses, these nodes can build arbitrary topologies. For example, here's just one randomly created one. And if we do not take proper care of this, it can easily happen that these topology malform. For example, that the diameter gets really high, or the degrees of certain nodes get really high, or there's some bottlenecks in the network. For example, if we take this node B13 out, this node here would be isolated. So we are interested in algorithms which can take such an arbitrary initial overlay and very quickly transform it into a nice overlay. For example, in a butterfly network, but also trees or expanders work. So the idea is that we want an overlay which has a low diameter and a low degree, because in these networks, we can then easily route message to other nodes, we can sample other nodes, we can aggregate data, or whatever you want to do in a distributed system. Now, if we would not have this communication restriction of log n bits, this problem would be trivial, because what we could do is we could exhaustively always introduce all nodes to one another. So each node takes all the identifier it knows and sends it to all these corresponding nodes. If we would do that, after O of log n rounds, all nodes would know each other. So we had one big click. However, we would use linear communication per round, which is something which we definitely do not want to do. So, but still, this log n therefore provides a lower bound. So even if we do not limit the communication, we cannot do it faster than log n. The common example for that is like a line graph. There it actually takes log n to like let the two extreme nodes learn each other's identifier. So in the polylogarithmic communication regime, this problem has been considered, I think for the first time, almost 20 years ago by Englund et al. What they did is they presented an O of log n to the square algorithm, which could transform the network into a tree. This was then 2 years later improved to the optimal O of log n, however, not for arbitrary graphs, but for graphs without degree 1. So in these graphs, all nodes have a dedicated parent node to which they have already broken the symmetry. So this makes the merging steps much more easier, it makes the construction a bit easier. But still, O of log n is a lower bound also for these graphs, because, for example, the line graph still would be a graph without degree 1. But still, this cannot easily be extended. So then there was a 10-year gap, and then Gmi et al. Presented O of log n to the square algorithm, which was deterministic. And then only 2 years ago, there was another big step made by some authors of this paper. And basically, they presented log n to the power of 3/2 algorithm, which also constructed the butterfly network. And here now in this work, we finally reach the lower bound of O of log n. And in particular, we do it differently than all the other works, because we came up with a much more simple approach, or to put it better, we came up with a proof for the simpler approach. But more on that later. So what has been done until now was basically always the same algorithm, but with slightly different rules. So the idea in all of these previous algorithms was that the algorithm works in phases, and in each phase, we have some supernodes of a certain size. Supernodes themselves are big sets of nodes which act in coordination. So internally, these supernodes already form the topologies we want. And then in each phase, each supernode tried to find out if it neighbors other supernodes. So it tried to find out the identifiers of all the other supernodes, and then picked some of these other supernodes to merge with them. So by merging 2 or more supernodes group together and build another bigger supernode. And if all supernodes does it, we get fewer but bigger supernodes. And if we continue that for enough phases, we will end up with a single supernode, which then contains the topology we want. This idea, as you saw, can be quickly summarized in a few sentences. However, implementing these things and proving these things is quite difficult, because it requires a high degree of communication. Because inside these supernodes, there are already these butterfly networks, and they need to apply a lot of non-trivial techniques to get things done very fast. So already for this log n to the 3/2 bound, it was quite tedious, and to get with this approach to O of log n seemed to be much harder. So instead, we opted for something different and for something more easy. Namely, we just thought, what happens if everybody just uses random walks to connect to random nodes? And then over time, the graph should get better and better connected, so that after O of log n rounds, it should be an expander or something. And it turns out that's true. So to go into this more formally, we assume that we start in a constant degree, in a regular graph. In a regular graph, all nodes have the same degree. Namely, we denote this here as delta. Of course, if you have arbitrary input graphs, those graphs do not need to be regular, but they can easily be turned regular by adding an appropriate number of self-loops. Then, if we have such a regular start graph, what each node does, it creates 3 times delta divided by 8 so-called token messages. A token message contains the starting node's identifier and a counter, and nothing more. And then these tokens are sent around the network via random walks. That means for each token independently, a random neighbor is chosen, and the token is sent there. So for example, v4 creates a bunch of tokens with its ID in it, and then sends some of them to v5 randomly. Then v5 sends randomly decides for all tokens it receives, so it sent it, and for example, sends the token of v4 to v1. And v1 then sends it randomly to v6. And this continues independently for all tokens for t rounds. Later on, we will see that t can be chosen as a small constant. Then after these t rounds, we then use the token to create new edges. For example, each node, let's take v6, picks delta divided by 4 many of the tokens it received and sends its identifier to the origin of the token, basically saying, I want to create an edge to you, you create an edge to me. And by that, we create new edges. However, we need to be careful here. because it could happen that single nodes do not get picked in this process. Because, for example, the node v4, it could happen that all of its tokens end up at nodes which have more than delta divided by 4 many other tokens, and there's a non-zero probability that none of v4's tokens are picked. In that case, v4 would be isolated, and we would not be able to create a better overlay. However, by choosing delta, so the number of tokens and thereby the degree, big enough, in fact, we need to choose this as big as O of log n, then we see that with high probability, this does not happen. Then with high probability, all nodes and all rounds only have a logarithmic number of tokens, and everything works out fine. This actually was not proven by us. This is like an older result, which you simply could reuse. So then if all tokens are used to create an edge, then all the origins of the token connect back to whoever receives the token. So we have bidirected edges. And if all nodes do that, we end up with a graph of degree smaller than delta divided by 2. Because each node has 3 times delta divided by 8 many tokens, which result from the tokens it sent out. So basically, it sends the token somewhere, and the endpoint created an edge back. And also, it has up to delta divided by 4 many edges, which are created through tokens that node received. So in total, it's always smaller than delta half. And if now all nodes add another delta half or more self loops, we end up at the regular graph again, and then we can repeat the whole process. So our hope is now that if we repeat this process often enough, then after O of log n iterations, we end up at a pretty densely connected graph, which then has a low diameter, which we can work with. And it turns out that this is actually true. Let me now give you a brief overview over the analysis. First thing we need is some measure of progress. And what we use as a measure of progress is the so-called conductance. So the conductance of a set is defined as the number of edges that leave that set and the number of all edges that start in that set. So for example, in regular graphs, this is always delta divided by s, and the upper term simply counts the number of edges that go out. The idea is that if I have a set of poor conductance, this set is not well connected to the rest of the graph. And if all sets have a poor conductance, the graph is not very well connected at all. And this is exactly the opposite of what we want. And then the conductance of the full graph is then simply defined as the minimum over all the conductances. So the conductance can be seen as kind of the bottleneck. However, if we somehow manage to let this conductance rise over the iterations of the graph, we can see that if we ever arrive at a graph of constant conductance, this graph also must have a diameter of O of log n. And once we have a diameter of O of log n, we have 1, because then via breadth first search, we can build a tree. And based on the tree, we can build every overlay we want. So in fact, what we want to show is that with every new iteration of graph, the conductance of a set is rising. So the conductance of all sets are rising, and the graph gets better connected every iteration. To prove this, we need to take a closer look at what actually happens in a single set in a single iteration. So here we see a set S, which is connected by only one edge to the rest of the graph. So the set S has a very poor conductance. Only one edge is going out, and almost all other edges are going to other nodes within S. Now, what we want is that here, and this denotes the outgoing edge. So what we want is that many tokens leave over this edge, so these and stay on the other side, so that back edges are created. So basically, what we want is that node v2 and v3 here create tokens. These tokens go over this edge here, end up at the nodes here, and these nodes then create edges back to those original nodes. Because then what would happen is the number of outgoing edges, it would rise. And since the number of all edges in S stays the same, because in every iteration we have a regular graph, a delta regular graph, this can only mean that the conductance of the set rises. So a rising number of outgoing edges is equivalent to a rising conductance in that graph. So the question now is, how many of these tokens do leave the set and go over to the other side? And this is the tricky part to analyze. But luckily, all the heavy lifting has been done for us, because we could luckily reuse a result by Kwok and Lau, which they published on the APROX conference in 2014. Based on their results, we could show that if each node starts 3 times delta divided by 8 many random walks, the expected number of walks that leaves the set depends only on t and the conductance. So in particular, it is delta times s, so the number of all edges, times square root of t, times the conductance of the graph, plus the conductance of the set. This looks a bit complicated at the first glance, but it gives us exactly what we want. If we have a set of poor conductance, so which is close to the conductance of the overall graph, we see that the conductance of that set rises based on t. So if you choose t to be a high enough constant, it will rise by a constant factor. And if we have a set which already has a good conductance, so the conductance of S is much higher than the conductance of the full graph, then we at least know we do not get worse. And this is in fact everything we need. Because now we can show that in expectation, for all these small sets, or for all these sets of small expansion, many tokens go over this few edges that go out and end up on the other side. So in fact, over every outgoing edge, in expectation, square root of t many tokens go. And so for each edge, in expectation, square root of t many tokens end on the other side. So the overall number of outgoing edges rises also by a factor of square root of t, in expectation, that is. And if we can show that this indeed happens for all these sets, then this means the overall conductance of the graph rises up. And if that happens, in the next iteration, even more edges will be created. Because if the number of outgoing edges of all subsets rise, then in the next round, even more tokens will go to the other sides. And then even more edges will be created. So if we are somehow able to show that, then we are done, because then we have it that in each iteration, the conductance rises by a constant factor, and then after O of log n iterations, we end up where we want. However, showing that for all sets it holds that the number of outgoing edges rises is quite tricky, because if you look at a single set, all edge creations are independent of one another. So since each edges are created by independent random walks, all the outgoing edges of a set can be applied to the Chernoff bound. So basically, the number of outgoing edges is closely concentrated around the expected value. However, if we look at two sets which possibly overlap, we do not have independence anymore. So what we are left to do is that we need to somehow cleverly count the number of sets and then apply a union bound to show that indeed no set does not grow. And the classical way of counting the subsets of a graph would be via this binomial coefficient. So we say the number of subset of size k is roughly n to the power of k. However, if we would use that in our union bound, this would mean that we need to show that the probability that a set does not grow is smaller than n to the power of minus k times c. So it needs to depend on all the nodes in that set, which is not true. Because if you have a big set with many nodes, but only few outgoing edges, the expectation will only be concentrated around these outgoing edges and not all the nodes. So what we need to do instead is we need to count the number of cuts. And using a standard result by Kaga, we can show that if all cuts have a minimum size of log n, the number of cuts which are a multiple of log n are also bounded by a polynomial. So in that way, we can show that all cuts with have alpha times log n outgoing edges do not grow with probability smaller than n to the power of minus alpha. And since there are only n to the power of alpha of these sets, a union bound over all of them implies that all of these sets must rise. We must then additionally show that that also this minimum cut gets preserved over all the iterations, but that can be shown with similar techniques. So wrapping up the talk, we also looked at some applications of our problem. So we found spanning tree biconnectivity in MES can be solved faster now. And let me now, for time reasons, come to an end. We have seen a time-optimal algorithm for overlay construction. This algorithm is extremely easy to extend and implement because it only is based on random walks. And basically, that's what's done in practice anyway. And we found several applications to nice problems. For more details on that, please look in the paper. I'm out of time here right now. And the only thing left to do is to probably find a deterministic solution, as we are still heavily randomized. That being said, thank you for your attention and hope to see you all at PODC.